Good evening, everybody. There are still some people trying to enter the webinar, so I'll wait a little bit more until the list is clear, and then we'll start this session. Okay, well, there are 3 people still trying to get in, but let's start because it's past 7 o'clock. Welcome, everybody. Good evening. And today we have a DASH webinar about how to get more out of your data science in practice with real UMCG use cases. I'm Peter van Ooyen. I will be giving you a short introduction on DASH. And then for the rest of the evening, we have a guest host for this webinar, so I will introduce him later on. DASH is the Data Science Center in Health of the UMCG. I'm one of the people working inside that organization unit. We do a lot on different projects concerning data science within the UMCG. We run our own DASH projects where we help people out with their data science problems within the UMCG, try to help them further by getting realized what they want to do. We work on the community building, trying to get people together that are working on data science in the different departments of the UMCG. We're also an incubator for collaborations, for example, with companies, outside organizations, to work together on data science projects. We look at funding, not only funding on projects that we run ourselves, but we also can help you to find funding or to write your data science paragraph, for example, or work package in your funding proposal. We have the machine learning lab. I'm the coordinator of that part, where we actually have people working on data science projects. We look at needs assessment, so we're looking at what is needed in the UMCG. We also get that information from our think tank, consisting of people from all over the UMCG that discuss on what kind of things are needed in the organization to help us further in the use of data and to get into a higher level there. We also work on education. The webinars like the one you're watching now are an example, but we also do other things inside different parts of the universities, also for the University of Groningen in different courses, and also within the UMCG itself, different locations where we provide educational sessions. And finally, communication, so also letting people outside of the UMCG know what we are working on and that we are a hospital that's really looking into the new area of data science, AI, machine learning, and trying to apply that to clinical care. So that's in short an introduction to DASH. I see still people coming in, so we're even more than when I started. Tonight, your host will be Mark Veldkamp. He's a product manager at the IT Academy. Mark is probably better capable of introducing himself, but as you can see on the slide, this is what he's working on: digital transformation, artificial intelligence, on lifelong learning in the field of data analysis and data science and programming, and student collaboration in Bring Your Own Data and innovation hubs. And the Bring Your Own Data is one of the projects that you will hear about this evening. So with this, I give over the screen to Mark for the further introduction and the remainder of the evening. Mark, the floor is yours.
Thank you, Peter. Yeah, hello, welcome, good evening. My name is Mark Veldkamp, and as Peter said, I work as a product manager of the IT Academy. The IT Academy is part of the Hanze University of Applied Sciences. And yeah, today I'm happy to be your guide through this webinar. Yeah, about a year ago, I came in touch with Andre Capelle. He's an analyst at UMCG. And he said to me, yeah, today we generate more and more data. And the question is, can an analyst play a role in the processing of data? Yeah, the answer is, of course. Andre is right. Data or artificial intelligence is the most important technology at the moment. That's why I also put it on a slide. We are in the middle of the digital transformation, and yeah, the artificial intelligence is the technology that is developing very fast and also exponential. Of course, there are also more technologies, also in healthcare, like for example, 3D printing. But yeah, artificial intelligence is hot today. Yeah, and it's important for organizations like UMCG, and also for individuals to gain knowledge of these technologies. Yeah, to stay and to stay fit for the future. And one of the possibilities to gain more knowledge about those technologies, for example, artificial intelligence, is to collaborate with students and lecturers from university. You have, of course, the Hanze University of Applied Science, but also the RUG, of course. And I want to highlight two topics about that. First topic is lifelong learning. Lifelong learning it's on the national agenda, and it's also a hot topic for universities. We should help individuals, professionals to stay fit for the future and gain new knowledge and skills about, for example, those technologies. And at the IT Academy, we developed in collaboration with organizations in the northern region programs like data analysis, data science, and programming, for example. And yeah, it's not an accident, not coincidence that it's also are very popular programs now for the reason I mentioned before. And the second topic I want to highlight is the student collaboration. Students have new ideas. They are familiar with new tools and techniques. They get lectures about it in the programs. And as a professional or as an organization, it's a chance, I think, to collaborate with students. And also a possibility to gain new knowledge. You can work in collaborate with students in innovation hubs where they can work on assignments or work on new tools, techniques, or they can be used like for field testing. And the other, and that's also the case today, is a bring your own data sessions, where students, professionals, and lecturers work together on a case. And our first case is an example of a bring your own data session. And I will going to hand over the floor to Jennefer and Wynand, who will present their experience of the case. But before we start, I think I hear no sound, so the microphone is on mute. And if you have questions, yeah, raise your hand in the right under the screen, or type a question in the chat. After the first case, we will have a few minutes possibly to answer some questions. So, and yeah, then we'll pick it up. And of course, at the end of the second case, there was also possibility for questions and discussion. So Jennefer, I would like to hand over the floor to you.
Thank you for the introduction. So yeah, the first case. So from a paper jungle to digital tranquility, how to get your data organized. So at the moment, for some of our processes, we are kind of in a paper jungle because we have a lot of people coming and writing down the usage and yeah, so if you want to filter on certain things, you need to read through all the different entries, and that can be confusing and is a lot of hassle. So to give a little bit of background, we are a research sequencing facility for next generation sequencing. And most of the time, this process looks something like this. So you have a biopsy or harvesting of your cells, to which you do a DNA or RNA isolation, to which you will quantify the DNA and RNA and also do a integrity control. So you know how much input you can use for your library prep, and to which you will need to do a purification and size selection, to which you need to do a QC and a quantification of your samples, so you know how much sample you need to dilute and also pull together, so you have the correct ratio and also get the amount of reads that you're expecting out of the sequencing. And a service that we can also provide is demultiplexing and alignment to the reference genome. And the problem that we're having regards these two processes, so the RNA integrity control quantification and the QC of the library pools. So in the old situation, we used to have the bioanalyzer as the device for these two processes. It is a low throughput device, so you have 11 samples that you can run, and it takes about an hour to be processed. And after that 1 hour, you need to have this hands-on time again in order to start a next run of, for example, up to 11 samples. This is very inconvenient because most of the time people have 12 samples. And then this device also had a medium difficulty regarding the handling. So you have this chip to which you needed to add a gel, to which you need to add a marker and also your sample and other things going on. This resulted in that not a lot of people wanted to be trained to this device. And because we were recording all the usage of this device on paper, this was fine since not a lot of people were using this device. But then at the end of 2019, we got this new device, the tape station, which is more high throughput. So it processes 96 samples in 1.5 hours. So to put that into perspective with the other device, that's about 11 samples in 11 minutes. So that's that's way better. And you also don't have this extra hand-on time in between these samples. It's easier in handling. So you have your plate, you put your sample buffer in there, and you add your sample, and that's it. So this is more interesting for people to be trained on. And at the moment, we have more than 30 people who are trained to this device. And as you probably guessed, we are still tracking this on paper, which is now becoming a problem because this is not sufficient in tracking who is using what amount of reagents, but also how many samples people are running on this device. So it now, at the moment, looks kind of like this. So this is all the different entries that we would like to know. So which date people are running, what their name is to correspondate or to correlate who is doing what, and also what amount of samples they're running and that kind of stuff. But because of device usage, we also would like to know if there was any complication with the run, so we know how to troubleshoot it for later. And what we now do is we type this over in an Excel sheet. This was the best at what we could came up with. Yeah, so it looks like this, and this is not the solution that we were hoping for. And as you can see, so on one day there were already 4 people who run on this device. So you can imagine that there are a lot of usage. There is a lot of usage of this device. So it takes a lot of time to type everything over. It is error prone, so people can maybe have a bad handwriting that a 6 will appear like a 5. But also we can make typos, and that's also not ideal. So at the moment we have this Excel sheet and we're not happy with it because it's not working. We know that it should be possible to have this database where you can just filter through things. But we need help with that because we don't have the knowledge on how to realize this. So we went searching for possible solutions, and most of all, first for the existing solutions. We asked other facilities if they were having the same kind of problems. Some of them replied, and it appears to us that different facilities use different applications for this, but they are not really happy with the usage of the certain application. So we felt like this was not the solution for us. So then we looked if there's maybe support within UMCG for something like this. And last year I actually watched the webinar from Dash like this, and I got interested in them, and I contacted them and asked if they maybe could be any services for us, and they got us in touch with the Hanze University. So this was the deal. So the direct application for us with this database will be to make it easier to make quotations. And the wishes that we have for the database is that it will be user-friendly, because a lot of different users will be using this, so it should be intuitive on how to use it. People from outside the UMCG or the RUG should also be able to use it. It should be a fair database, so that the data that will be entered will be in a uniform way. So you don't have 2 different values meaning the same thing. There should be an ability to filter through the data, so you don't have to read through all the data in order to get an answer to your question. It should be easy to manage ourselves. preferably no subscription fee or something like that. It needs to be secured, and it would be nice if there is flexibility into the integration of other applications. And possibly for the future, we could maybe add a run scheduler so that people can schedule a run behind their own desk. For us, it would be nice to get a notification when certain reagents are maybe out of stock, and get a reminder that, well, maybe you need to order new reagents, so that we don't have to look into the actual cabin each time to see if there is still enough. And another possibility is that we maybe can chain other devices to the same database. So for example, for the process of QCing the library pools, we also use a qubit, and well, maybe we can use this database for that as well. And then I will give the floor to Wynand, and he will talk about how they approached this problem.
Yeah, thank you, Jennefer, for the introduction and the nice statement of the problem that you had when using your data. Yeah, the way we approach these type of problems, because Jennefer was not the only one with these type of questions at the Hanze University, is to organize bring your own data or BIOD sessions. And these sessions are really designed to help people, well, but typically the problems that Jennefer described, but also other data problems that they may have. I'll show a few examples later on. And what we want to do in those BIOD sessions is to really look at the data that people have, really their Excel files, or in this case the paper files, and do a hands-on analysis of the data. And it can be a very complicated analysis and making a very complicated model, but it can also be an analysis in terms of you have to store your data in this particular database, or you have to reorganize your data in this way in order to make it work. We do this typically together with the team, in this case from UMCG, Jennefer and Diana was also involved, and a team of students and teachers from the Hanze University. Based on the complexity of the problem and the scale of the problem, we assign students, teachers, and we make the team smaller or bigger. And then typically what we want to do is to have these sessions well, you have to think of sessions of an afternoon or an evening, where we discuss the data and come up with an approach and come up with an answer. So our aim is really to at the end of those sessions to leave with an answer. And those answers can be like, well, what I already said, a very complicated software model or an algorithm. It can be an advice on how to treat your data, or it can be something that we say, hey, we should collaborate on this more, we should do a pilot study, or we should get funding together to approach these problems. So it's really meant to be informal, low, laagdrempelig, I don't know the word there, but with a low barrier of entry, just discuss what you have. So what we do in those, and Jennefer already explained, in this particular case, we were interested in making data fair, making a fair database. In this in all BIOD sessions that we have, people come in with different types of problems that can be in the entire chain of data analysis, which is shown here. It can be on the left-hand side, the generation part. We have lots of data, we don't know what to do with it, to the very end, where we have organized the data and done statistical analysis, and we really work on making advanced prescriptive models, machine learning models, etc. So anything goes in these BIOD sessions. So it is also an invitation to people who are listening and have their own data set, data problem. Feel free to contact us and we can talk about it. Well, in this particular case, we are even on the left of this picture because we started the paper trail, in fact, as Jennefer explained. And what we want to do is in the first place make these data understandable. Jennefer talked about the quotation system, but in the end we want to build on to this fair database that we're creating to also maybe do some kind of analysis on the data that are being generated. So I'm now going to, so this was a bit of an introduction, a general introduction on the BIOT sessions, and I'm now going to focus on the particular session with Jennefer and Jana from ERIBA. And what we had a team of 6 people. We had 4 people from the Hanze, 2 students who are also in the audience this evening, a teacher, and myself was also involved, and Diana and Jennefer from ERIBA. And the idea is, of course, to have a free format discussion on how we should approach these data. We had that meetings as well. Normally we have them in really an informal style with pizza meeting style, but obviously under these circumstances we did everything online, which made it a little bit more difficult, but I think we managed to exchange all the data and information that we wanted to exchange. And what we found out after those 2 meetings, that the biggest win in the case of Jennefer described, and she already alluded to that herself as well a little bit, is the organization of the data, and going from paper to not only to Excel, to an even better organization. Sorry? Oh, there was an echo here. Okay, so what we really need to define what kind of data types do we have. We have researchers, we have cost centers, so the numbers where the money is coming from. We have actual data that we're generating, lab kits, etc. And also we need to think about what kind of values can these data have. What do we mean by a researcher? How do we identify a researcher? By his name, her name, by an email address or a personal number, etc. So we really needed to think about what kind of values can these data have, and how can we standardize that. That's the middle column there. And then maybe an even more important thing is, what is the relation between the data? An experiment has many runs, for example, and an experiment always needs a cost center and a principal investigator. And these kind of relations you want to have in your database, so that you know, when I do an experiment or when I do a run, I have all the data that are required to later on, well, do the quotations or do the billing, but also maybe to do a part of the analysis already for the researcher, for example, quality control or QA on the data. And so when you look at these columns, you may wonder, well, it's a lot of data handling. It is almost maybe a little bit boring. It's organizing data. And indeed, sometimes that is a boring task, gathering your data, cleaning your data, but it's the most important part of a lot of data analysis projects. And I think that was really well explained as well by Jennefer in her introduction. So we spend a lot of time. So we decided in the second BIOT meeting, let's make this a student project, because we have students at the Hanze who know how to deal with these kind of things, and also to process these data in order to accommodate the wishes that Jennefer listed. So I'm going to show a few results of that. The project is still ongoing. We started in January, and we have to accommodate that, of course, also in the schedule of the students. But the first thing that was done was to create a relational database. As I explained in the previous slide, we really define what kind of data we have, and also what kind of values these data can have. So, for example, an email, if we, I'm going too fast. So what we see here on the left-hand side is basically the textual representation of a database. This is a textual representation of the data that we have and that we're going to work with. So I'm not going to explain all the tables. That is beyond the scope of this evening. But what is important here, for example, if we look at, I'm not sure whether you see my mouse, but for example, line 16, we define a sample number, and we define that this sample number needs to be an integer, so it needs to be really a number. You're not allowed to type in anything else there. And if you, for example, on line 9, we identify a researcher always with his or her email address, which needs to be typed in letters. It cannot be any numbers, for example. So this is how we define the values that we want to have in the database, and also how these values relate to each other in tables, and also what kind of things we want to store in these tables. And this is quite a bit of work, and it also required iterative input from Jennefer, like, hey, we want to do this like this. What do you think? Do we need more data in order to organize your run? So it's an iterative process, and in the end, we managed to organize the data in a useful way. And once you've done that, and that's very important, I think, that's the hardest part of the work, because after that you can really easy or more easily write the standard forms that Jennefer was alluding to in a web form. So I have an example. So what we did, we took the data. I hope this is visible. It's a bit small now, maybe on this screen. But what we see here on the left-hand side is already a website. So not an Excel file anymore, but a website that you can in fact go to. You can log into that website, and you can enter all the data that are needed to properly start a run. So your email address is required, your name, your institute, etc. So this is already a working web form in which data can be entered and saved. And once you enter the data in these web forms, it's stored in the database, so it's stored also in a secure way, and it can be retrieved from the database anytime in any format that you want. So for example, we have made a small export on the right-hand side. There's a typo here, it should be tape station, of course, not tab station. Where you can see which runs and which tracking IDs have been processed at which dates. And we left out a few more details of those runs because they're not important right now. But you can, in this way, enter very structured your data into the database, and you can retrieve any data from the database also via a web form. So I don't have the wish list here at heart, but from Jennefer, but this web form, this structure, does not need any software licenses. It's all open source, and it's very easy to run from within your own laptop. So it's very lightweight to use and easy to install. Because we store it in a database, it's also easier to secure these data. We can manage who has access and who doesn't have access to certain parts of the database. And that's also very important, of course, these security and privacy issues that are related to the data. So this is in fact where we are at this moment. This project is still ongoing, and the students are working on it, and we have regular feedback from Diana and from Jennefer on what we're developing. But because of the time, we don't have opportunity to go into all the details of the database that is underlying this web forms that you see. So I just want to spend one slide on the future. We have a prototype of the web form and the database working at the Hanze University. And the next step is to make that system available at ERIBA, at the sequencing center, to in order to make it useful for them at this moment. And in the future, we will, whenever we have time, make the following additions to the system: the scheduling of the runs, alerting systems for reagents. And we are very curious to see whether we can use the same system. It's a very generic system to attach to other devices, maybe not only at ERIBA, but also other people who have the same issues in managing their laboratory control, laboratory flow of data. Later on, it's also an ambition, I would say, and maybe we can take this a new project to make the actual sequence data sets that are being used searchable, the metadata of those sequencing data sets, so that you can easily see how many data have been used on which model organisms or on which cell types, etc. To make it a bit more, bigger and more broadly useful. And maybe also, once we have organized the data in this way, add simple or more complicated analysis tools to the data. So can we do an automated QA/QC on each run and write and send a report to the researcher? Or can we already do some analysis if the researcher provides metadata on the grouping of the samples, etc. So these kind of things are all possible in the future, but it starts, of course, with a good organization of the data that go into the system. And I think we have made the first steps towards that goal in this particular project. Last slide from Jennefer and me. Some take-home messages. The BIOT, the way people can bring in their data and discuss what is possible with their data, is a very nice way to explore the data, I think. And there's really no limit or no prerequisite on the data that can be brought to the table in these sessions. As you saw, we can start with paper data and make something very useful out of it. And the more people have that have a look at those data, the more possibilities and ideas we get. So those are always very productive meetings. And we are very happy to, Jennefer and Diana had this vision, we want to have it like this, we want to build this system that does this and this and this, can be combined with the know-how and the existing technology that we have. So in this case, a very fruitful collaboration. I will leave it at this because of the time, and Jennefer and I are happy to take, I think, any questions at this moment. Mark, I give the floor back to you.
Okay, thank you, Wynand. Thank you, Jennefer and Wynand, for this presentation. And it's great to hear that you're still working on this project. And yeah, it's a beautiful example of how Jennefer, as a research technician at ERIBA, can collaborate with students who are also in the public tonight. And of course with lecturers of the Hanze. So yeah, really great. Looking at the time, I think we're still on a tight schedule, but maybe there's room for one or two questions. Is there a question? Maybe you can put it in the chat. Of course, we can also wait for the end of the session. Okay, no questions at the moment, so then we will continue. And yeah, if a question pops up, so maybe you can yeah, keep it for the end of the session. And then we'll go to the second case of tonight, of this evening. This is a case, is a beautiful example about a collaboration with DASH. Ineke Riphagen, a clinical chemist in training and a postdoctoral researcher, works on the interpretation of urine steroid profiles. And this is a very complex process. And while Ineke was working on it, she thought, hey, can we use technology to make life easier Yeah, that's why she contacted Dash, and yeah, Dash connected her with Eline Meijer, who's a student human-machine communication, and yeah, she helped Ineke with the development of an algorithm. And yeah, I think this is a beautiful example on how you can use technology and benefit from technology. So for the second case, I will hand over the floor to Ineke and Eline.
Thank you for the introduction. We will present our case study, the development of a machine learning model for interpretation of urine steroid profiles. First, I will give a short introduction, and then I will discuss the process of the development of the machine learning algorithm, including the data collection, and Eline will discuss the processing of the data, the training and testing of the machine learning models itself, and how to choose the best model. And finally, we will go a little bit further into how you can get insight in how this machine learning model works. What is in this black box? During urine steroid profiling, we measure 33 different steroid hormones and their metabolites, which are mainly synthesized in the adrenal glands. This figure shows a schematic overview of steroid hormone synthesis. All of these hormones are derived from cholesterol and are converted into active hormones through many different enzymes. A measurement of these steroid hormones and their metabolites provides useful insight into the synthesis, metabolism, and excretion of these hormones, and may reveal underlying enzyme deficiencies or diseases that are associated with steroid hormone overproduction. Well, clinically, urine steroid profiling is used for diagnosis and monitoring of various adrenal diseases, such as adrenal tumors, including malignant adrenal tumors, the adrenal carcinomas, or benign adrenal tumors, the adrenal adenomas, and as well as various inborn errors of steroids synthesis due to enzyme deficiencies. Well, this is an example of the way we are currently reporting the results of those urine steroid profiles. We report the excretion of the individual hormones, as well as a couple of diagnostic ratios, and we interpreted these results manually. However, we were wondering whether we could develop a machine learning model that could aid in the interpretation of these urine steroid profiles. Well, since the prevalence of these adrenal diseases is very low, we used existing data sets for the training and development of the machine learning models. These data sets consisted of over 600 subjects with verified adrenal diseases, including adrenal tumors or enzyme deficiencies. We also used data of healthy subjects of the Lifeline study population. However, since large data sets are necessary to train the machine learning algorithms, we extended these existing data sets with data that are extracted from our laboratory information system. And so in total, we used around 1,200 urine steroid profiles for training and testing of our machine learning models. And it's important to notice that most of the included steroid profiles are of normal, healthy subjects, and that we included also some conditions that are very rare. For example, a pore deficiency or a combined 17-hydroxylase and 17-20-liase deficiency. And now Eline will take over.
Yes, so to develop the machine learning model, of course, we needed some data processing, and of course, data set had some limitations. Some values were missing, or some measurements were non-detectable, so they were below the detection limit. We labeled all those missing samples as 0. This also corresponds with the way clinicians and analysts approach these values. So for a machine learning model, it will approach these values the same way. Therefore, they will labeled as 0. And of course, the data samples were also labeled in specific ways, because the goal of the machine learning model was to give an advice whether the sample had a specific diagnosis or was abnormal or normal. Therefore, we developed a binary classifier classification of each data sample, because each data sample had a label with normal and abnormal, and if the data was abnormal, it also had a disease-specific class label. Yeah, and these labels you could see in the previous slide. So about training our machine learning models, we actually trained a two-step model. First of all, the most important thing is that you would classify as an advice the normal from the abnormal samples, profiles, and therefore the first step would be a binary classifier, and the second step would be to classify into a specific disease diagnosis. And that also, well, we developed that also in our machine learning model. Before we train our model, we divided the data set into a 80% training set and a 20% test set. It's important for a machine learning model to be tested to test in independent samples, so samples that they wouldn't see before, and train on a specific set, so they would not be seen yet by the model. And the second thing is that we included 33 steroid metabolites measurements. We included the age, the gender, and whether someone would take birth control pills, because that also influences your hormone levels. And as Ineke might have said, they also used ratios to classify data, urine profiles, but these ratios should not be included for the model, as they would not be independent of the steroid metabolites, because they're actually based, these ratios are based on the measurements of those 33 steroid metabolites. So it would only make the model more complex, and you would like to have a model that is as simple as possible, but explains the most of your data. We tested several machine learning models because beforehand you have a new data set and you might not know which machine learning approach is the best possible. So we tested several machine learning approaches, and we actually looked at the general performance of the models, the accuracy, how many did they actually classify correct. We looked at the precision, which of all the positive positive predicted samples are actually really true. And we also looked at the recall, and that is quite that's also the sensitivity of the model, and that's quite important because the higher the recall is, the lower the false negatives are. So for example, for the binary classifier, you would not, for the goal, you would not like to miss abnormal samples, because classifying someone as normal, and if that person is really sick, that would be harder. That would be a harder mistake than the other way around, because you would look into it further. But we did not only look at the general performance, we also looked further than the general statistics, and we also looked at the type of mistakes, because the general performance of the model may not say everything about the performance, and I would like to show you that with the hand of the performance of the different machine learning approaches on the binary classifier. I will only discuss the binary classifier today, how we choose that, because the multi-class classifier we decided on the same in the same way, but for the time being I will only discuss the binary classifier. So for the selection of the binary model, the first step of the clinical classification tool, we tested 4 different machine learning approaches. For the time being, I will not explain how these approaches all work, but they are quite different. And in the we tested a support vector machine, a random forest, the RF XGB boost, and a neural network for this study. And in the table at the right bottom, you can see actually the performance, the general performance of each machine learning approach. And you can see actually that all the accuracy, the precision, and the recall are quite close to each other. And there isn't much of a difference, but we eventually choose the neural network. And that is because we looked at the type of mistakes. So as I told you before, every data sample has 2 labels, one binary and one multi-class, one disease-specific label. And as you can see, all the approaches, except for the neural network, made especially mistakes on one specific diagnosis, and that's the 11B HD type 2 deficiency. That is a type of enzyme deficiency, and the neural network only made mistakes on the non-functioning adrenal cortical adenoma, and this non-functioning adenoma is a sort of special category, because it's quite harmless to people. And if you misclassify someone with a 11B HSD deficiency, it's way worse than a non-functioning adenoma. So we eventually, although the neural network had not the best general performance, we did choose the neural network because of the type of the mistakes. So that's something we did, and we looked further than just the normal performance, and really looked at the data. What is important for this goal of the machine learning model, and what would we want with it? So another thing is machine learning models. Artificial intelligence is something quite unknown to us. We don't exactly know what is happening inside that black box. We just know the data we put in a machine learning model, and we only know the outputs. So we put in a whole data set, and we just let the model learn something, and we act on what it predictions are, or its classifications, its decisions. But especially in healthcare, you want to know something. If you make a diagnosis, and you have an advice from a machine learning model, you want to know if you can really rely on that advice, if it's really means something. So you want to know what's in that black box, that machine learning box, and therefore it creates, if you look into that, it creates trust among users. You might get insights on possible improvements, because you might know why a machine learning would make certain decisions, and why it would be maybe wrong or right. And you also get insight on the future importance. So if you make a machine learning that's really good, you might actually learn something, and learn maybe something about the underlying patterns in your data. So that is why we created a machine learning model that gives an advice, but we also implemented an explanatory model. And we did that using Shapley additive explanation, SHAP values. It's a tool to explain a machine learning model, and to really look into that black box. I will explain a bit how it works by its example. For example, you have 3 persons, Anne, Bob, and Cindy, ABC, and these friends hammer the airlock into the ground all together. But you want to know which person actually contributed the most of it, which feature in your model is of most important to your model, and what is the reason why a model makes a certain decision. And that is what SHAP values are. They give the marginal contribution of each feature, and what a SHAP value model actually does, it tries all the combinations of whether a value is present or not, and it calculates the end error, and it takes the average, and that is the marginal contribution of each feature. So as you can see, this is only actually a sort of model with only 3 features, 3 persons, and you can also see that the explanatory model already creates some 8 different possibilities. If you have more, it exponentially grows into how many combinations it is. So you can imagine how computational, how hard it is. But they actually made a approximation Lundberg and Lee, who designed this, actually made a library for this, which you can use. But what's most important is that the SHAP values indicate how much a feature contributes to the target value. This could be positively as well as negatively, because sometimes a feature indicates that a urine's profile is really normal, but sometimes also that it is really abnormal. So it could be either positively or negatively. But the bigger the SHAP value is, the bigger the contribution of the feature. And so if we look at the SHAP values of the neural network from the binary classification, you can see on the right figure, you can see the mean absolute important SHAP values of each feature. Here, all the features included in the model are listed, and on top is the most important feature. These are steroid metabolite measurements, metabolites, and you can see also the age, which is also quite important. You can see that's back in the decisions. And the color on the left, you can see all the dots are specific SHAP values for each prediction of the model. And the higher the SHAP value, the more to the extremely right or extremely left it goes, and to the right it indicates a more normal profile, and to the right a more abnormal profile. And if, for example, the steroid metabolite measurement is quite low, the dot is blue, and if the measurement is really high, the dot is indicated as a red one. So you can see sort of the correlation between if a future value is high, then it would be indicated as abnormal by the model. So you can really see the correlations between a model and how a model makes its decisions. And if we look further into this, we can see, for example, that the neural network was really well at classifying the 11B HD type 2 deficiency pretty well. You can see this back actually in the SHAP values, because as you can see in this figure, if someone has a deficiency in the 11B type 2 deficiency, this part is blocked, and you would get an increase in the metabolites of THF and allo THF. This is a 5-alpha, but it is the same as a allo THF in this figure, and a decrease in THE, which you can also see as a second one important value. So you can actually see that the model is basing its decisions on a underlying pattern, which you can also see back in the physiological process of something. So it really gives some clinical information about how it's making its decision, and that could be really helpful in this case. So this is sort of a discussion. So what is important to remember is that the input determines the output of a machine learning model. It's good to know which features do you include in the model, what's of importance, and especially for a clinical assisting tool, you want to know, you want to give the machine learning model the same information as you have, but don't make it too complex. Just make it a bit easy, because it's easier to interpret also, and look further than only the general statistics. And that's what we did. And we also use SHAP, and that proved really helpful in this study because it creates trust. It gives us insight on possible improvements, and it gives us insight on feature importance. And I think this study is a really example of how we can use data to get more insight on how certain processes work, and how machine learning can be of help as a clinical assisting tool. So that was the take-home message for today, and I would thank you for your attention, and if there are any questions, please give them in the chat or raise your hand.
Yes, thank you, Eline and Ineke, for sharing this experience with us. And yeah, I think it's a great example of how to use machine learning. So yeah, thank you for this presentation. For now, we can go over to the questions. The first questions are already in the chat, and I will start with the first question. And I think this is a question for Jennefer and Wynand. It's from Wim Krijnen, and he asks, can you say something about multivariate techniques? Wynand, is it possible to say, or Jennefer? Yes.
Yeah.
I'm not sure what you mean by multivariate techniques. Is it something? Is it a question for me, or is it a question for Wynand?
I think it's more for me, Jennefer. If I look at the question, so and I saw that in the chat. Yeah. So because in one of my slides, I think in the second slide where we go from data from separate data files in Excel to consolidated data, and then to the statistics where we do multivariate analysis. We do more classical univariate analysis, and the multivariate analysis that we do, and I think that was also a bit highlighted in the last talk that we saw, is a bit dependent on the problem. But if we talk about unsupervised multivariate analysis, we often use things like PCA and PCR, hierarchical clustering, the standard pattern recognition techniques to see what kind of patterns are in the data and what are the main experimental factors that shape the patterns in these data. And a bit dependent on what type of data we have at hand, we do various kinds of normalizations and log normalizations to get the data into better shape. So it's basically very genetic multivariate techniques there. Okay.
Okay, thank you, Wynand. The second question was also from Wim, and I think it's for Eline. Does logistic regression really fail in diagnostic accuracy? You really need AI type of techniques? Eline, can you
Yes.
maybe?
Does logistic? Well, of course, you can also use logistic regression. However, I think that AI techniques are a bit better in performance. I also used my machine learning model to adjust that it would not create as much as false negative profiles as a logistic regression might do. So I think you do really need AI, but I think the AI models are also doing a bit of logistic kind of regression.
Okay, Eline, thank you for your answer. Are there any more questions? This is your chance to put them in the chat. I'll wait a few seconds.
Or maybe we have people listening that hearing the presentations today think, hey, I have some problem myself that I would like to have solved.
Yeah, maybe we inspired some colleagues to share their challenge with Dash, and yeah, maybe that will be a next case to work on. So I think the presentations were quite clear, and yeah, you can. Oh, we have a question from Jitka. Can any researcher from the UMCG be invited to bring a problem to BIOT? Are there financial restrictions?
I can say something on that, Mark. In principle, there are no financial restrictions or any barriers in principle to bring data to the table. The only thing that that we need to see are the actual data. So if there's any privacy concerns, you have to be careful. But you often can circumvent it as well by just giving a general description of the data or by anonymizing part of the data. But other than that, there's no initial financial restriction. Of course, if we see that the data is so complex that it will take 4 months for a person to work on that, we need to either apply for funding or to find an arrangement with a student or what have you to make that work. But anything goes there.
Yeah, and in addition to that, I would say first contact Dash because they first do a kind of an intake conversation, and they can help you any further.
Yeah, so maybe I can comment on that. If we get a request, since the beginning of this year, we started using a so-called machine learning canvas. So when we get a question, then we'll go through that canvas, and it gives us a first idea of what the problem is and what the possible directions could be to solve it. And based on that, we will see how we can proceed. And we had discussions also with Mark earlier to see to also link that to their students to try and get that synergy going.
Okay, before we close this sessions, maybe Peter, you can say some last words, and maybe you can go for talk about the next activities of Dash.
Yeah, thank you, Mark. I would like to thank all the presenters this evening. Were very nice presentations and interesting projects that we did. Mark, thank you very much for being the host for this evening's presentations. And also introducing the way that we can collaborate. If you want to get in touch, like Mark already said, you can contact Dash. You can get through to us through our email at dash@umcg.nl. We also have a page on the new UMCG research web pages. You can access us to LinkedIn. These presentations were recorded and will be available through our YouTube channel. And I think finally we have information about our next DASH webinar. That will be on machine learning applications in radiology. And there we have speakers Christian Garbin and Auger Manquet from the Florida Atlantic University. Auger Manquet is a well-known educator in the field of AI and machine learning in radiology. He runs very interesting courses on that topic. And he's well known all over the world for his teaching. So we are very happy that we have him to present for a DASH webinar on his experiences with machine learning in radiology. So that will also be a very nice webinar. Again, it will be at the end of the afternoon, so from 4 till 5. It will be on April 20th. So everybody is well invited, and also invited to spread the word and have more people join that would like to be there in the audience. So with that, I think I can close this session for this evening. Thanks again to all the speakers. Thanks, Mark, for running the whole show today. And
yes, you're welcome.
Okay. And then we hope to see you all in April again. Thank you very much.
Thank you very much.